Today, we'll take the next step in understanding inequalities by learning how to graph them. Previously, we discussed solving inequalities algebraically. But what if we want to see all the possible solutions for two-variable inequalities on a graph? This is where graphing inequalities becomes really useful. By the end of this video, you'll know how to represent inequalities in two variables visually to capture all solutions at once. Let's jump in and see how this works. Graphing an inequality allows us to see the entire range of solutions on a coordinate plane. Each inequality will divide the plane into two regions. One where the inequality is true, and one where it isn't. Our job is to identify and shade the region that represents all possible solutions. Here are the key steps to graphing linear inequalities in two variables. Start by rewriting the inequality in slope-intercept form if it's not already in that form. This makes it easy to identify the slope m and y-intercept b, which we'll use to draw the boundary line. The boundary line represents the equality part of the inequality. For example, if we're working with this expression, the boundary line is y equals negative 2x plus 5. The type of line we draw depends on the inequality symbol. We use a solid line for greater than or equal to, as well as less than or equal to symbols. This means points on the line are part of the solution. Meanwhile, we use a dashed line for less than or greater than symbols. This means points on the line are not included in the solution. After drawing the boundary line, we need to identify which side of the line represents the solutions to the inequality. A quick way to check is by substituting a test point, like the origin, into the inequality. If the point makes the inequality true, shade the side that includes the point. Otherwise, we shade the opposite side. The shaded area on the graph represents all the points that satisfy the inequality. This is what we call the solution set. Knowing how to interpret this visually gives us a powerful way to see every possible solution for the inequality. Let's practice this method with some examples. Let's graph this inequality on a coordinate plane and identify the solution region. In this case, the inequality y is less than x plus 2 is already in slope-intercept form, where m is 1 and b is 2. This will make it easy for us to plot the boundary line. The inequality symbol means that we'll use a dashed line because points on the line itself are not part of the solution. Now, let's graph the boundary line. We start by plotting the y-intercept at 0, 2. This is the point where the line crosses the y-axis. With a slope of 1, we know that for every 1 unit we move right, we move up 1 unit. Starting at 0, 2, we move right 1 unit and up 1 unit to 1, 3. Next, we connect the 2 points using a dashed line. This represents the boundary line for our inequality. Remember, we're using a dashed line because of the strict inequality symbol, meaning points on the line are not included in the solution. Now, we need to determine which side of the line to shade. To do this, let's substitute a value into the inequality. The origin is usually a convenient test point, unless it lies on the boundary line. Since the origin makes the inequality true, we'll shade the region that includes this point, which is below the line. Our graph shows the solution to y less than x plus 2, as the region below the dashed line. This shaded area represents all points that satisfy the inequality. Great job! Let's try another example. Which of the following inequalities represents the shaded solution region for the graph below? Our first task is to determine the equation of the line. Since no equation is given, we'll use the graph to identify the slope and the y-intercept. We can see that the line crosses the y-axis at y equals 3. This point is the y-intercept, so we know that b is equal to 3 in our equation. To find the slope, we'll look at 2 points on the line and determine how much y changes for a given change in x. Let's pick the y-intercept at 0, 3, and another point where the line passes exactly through the grid, like 2, 2. Moving from 0, 3 to 2, 2, we see that y decreases by 1 unit while x increases by 2 units, giving us a slope of negative 1/2. This makes our boundary line equation as y equals negative 1/2 x plus 3. Next, we'll check if the boundary line is part of the solution. Since the line on the graph is dashed, this means points on the line itself are not included in the solution. Therefore, we're looking for an inequality with either greater than or less than. Our final step is to identify which side of the line to shade. The region below the line is shaded, so this corresponds to values of y that are less than the line's equation. This indicates an inequality of the form y less than negative 1/2 x plus 3. To verify, we can substitute the origin into the inequality. If the origin makes the inequality true, then the shaded region, which includes the origin, is indeed the solution set. Since the inequality is true for the origin, this confirms that our inequality is correct. Let's look over the choices again. We can see here that the correct inequality that represents the graph is choice A. Great work today! Let's quickly recap the main concepts we covered for graphing inequalities in two variables. Start by rewriting the inequality in the slope-intercept form if it's not already there. This makes it easy to identify the slope and the y-intercept, so we can quickly graph the boundary line. When graphing the boundary line, we mainly use a solid line or a dashed line. We use a solid line for greater than or equal to, as well as less than or equal to symbols, indicating that the points on the line are part of the solution. Meanwhile, we use a dashed line for less than or greater than symbols for points on the line that are not included in the solution. To find the correct region to shade, pick a test point, like the origin, and substitute it into the inequality. If the point makes the inequality true, shade the side that includes the point. Otherwise, we shade the opposite side. The shaded region represents all possible solutions to the inequality. This is your solution set, showing all points that make the inequality true. With these strategies, you're all set to graph any linear inequality in two variables. Keep practicing, and soon these steps will become straightforward.